So here we have the integral of the integral of 4x to the fourth plus 27x cubed plus 60x squared plus 54x plus 18 divided by x cubed plus 6x squared plus 9x. And it's probably not a u sub. We could try letting u equal the denominator, but if u is equal to the denominator, the derivative would be 3x squared plus 12x plus 9. And I definitely don't have that or a nice integer or constant multiple of that up here. So u sub probably not the way to go. I would think about partial fractions, but before I can even think about partial fractions, I notice that the degree on top is larger than the degree on the bottom. And so to be able to even do anything, I really have to do polynomial division before I can do anything else. So that's our first step here, is to do polynomial division. It's not going to be particularly pretty. So we've got x cubed plus 6x squared plus 9x divided into 4x to the fourth plus 27x cubed plus 60x squared plus 54x plus 18. Okay, so we ask ourselves, what do you multiply by x cubed to get 4x to the fourth? And the answer is 4x. And we multiply this 4x by everything down here. So 4x times x cubed is 4x to the fourth. 4x times 6x squared is 24x cubed. And 4x times 9x is 36x squared. We subtract. 4x to the fourth minus 4x to the fourth is 0. 27x cubed minus 24x cubed is 3x cubed. 60x squared minus 36x squared is 24x squared. And we bring down the next term, 54x. And then we do it all again. So we ask ourselves, what do you multiply by x cubed to get 3x cubed? And the answer is 3. And 3 multiplies by all of this. So you get 3x cubed. 3 times 6x squared is 18x squared. And 3 times 9x is 27x. Subtract 0. 24 minus 18 gives you a 6x squared. 54 minus 27 gives you a 27x. And then we're going to bring down the 18. And we might be in luck. I don't know. Let's take a look. So what we're going to do is we're going to say we can rewrite this integral. This integral is equal to, I'm going to grab a new pen here. Less trash pen. This is going to equal the integral of the quotient 4x plus 3 plus the remainder 6x squared plus 27x plus 18 divided by the divisor, which is x cubed plus 6x squared plus 9x. Okay, so integrating this is not a problem, right? It's going to be 4x squared over 2 plus 3x. Integrating this is where we're going to have to do some more work. We might be able to do a u substitution now. I don't think we get to that. If we let u equal x cubed plus 6x squared plus 9x, our du is going to be 3x squared plus 12x plus 9. And to get 6x squared, we have to multiply this by 2. To multiply this by 2, you get a 6x squared plus 24x plus 18. So close, but too far. So we don't get to do a u sub here. We have to do other things to integrate this. So we are dealing with, I'm going to break this up into two intervals. The interval of 4x plus 3. I mean, let's just write that. What will you factor on x? Yeah, we're about to get there, Marshall, for sure. So this is going to be the integral of 4x plus 3 dx plus the integral of, in fact, let's actually factor out a couple things. So from the top here, I can totally factor out a 3. Do I want to factor? Yeah, I really do. So I'm going to factor out a 3. And I'm going to have a 2x squared plus 9x plus 6. And then the bottom, I can factor out an x, but up to x times x squared plus 6x plus 9. And x squared plus 6x plus 9 factors is x plus 3 quantity squared. So the denominator is really x times x plus 3 squared. And for this integral, we are going to have to use partial fractions. So we're going to set 2x squared plus 9x plus 6 divided by x times x plus 3 cubed equal to a over x plus b over x plus 3 plus c over x plus 3 squared. Questions about this before we move on? Okay. So then we're going to multiply both sides by this common denominator. On the left, we're going to get 2x squared plus 9x plus 6. On the right, we're going to get a times x plus 3 squared plus b times x plus 3 plus c times x. Again, we're just multiplying each thing by x times x plus 3 squared. When we multiply by a over x, the x cancels. When we multiply by b over x plus 3, one of the x plus 3 cancels. That should be a square, not a cube. When we multiply it by c over x plus 3 squared, the x plus 3 squareds cancel. You get c times x. And now we pick our convenient values of x. And there's two of them. The convenient values are x equal to 0 and x equal to -3. Picking x equal to 0, I get 0 plus 6 on the left. I get a times 9 plus 0 plus 0. So a is equal to 6 divided by 9, which reduces to 2/3. Okay. It might have, that's not a big deal. So then if I plug in x equal to -3, I'm going to get, let's see, 2 times, so -3 squared is 9, 2 times 9 is 18. 9 times -3 is -27 plus 6. I'm going to get a times 0 plus b times -3 times 0 plus c times -3. So I end up getting, let's see, -9 plus 6 is -3. So I get -3 equal to -3c. So c is equal to 1. And then finally, we need to find b. So I'm going to do the thing where I like to do is called equating coefficients. So I'm going to look for the highest power of x on either side. It doesn't have to be the highest, but usually the highest is the easiest. The highest power of x I see on either side is an x squared. So I have 2x squared on the left. If I look at the x squareds on the right, I will have an a times x squared. I will have a b times x, so a b times x squared. I will not have a c times x squared. So that means that 2 has to equal a plus b. But a is equal to 2/3. So that means 2 minus 2/3 has to equal b. 2 minus 2/3 is 4/3. Okay, so here's what we end up getting. Getting a place where we don't have enough room to write anything. So a is 2/3, b is 4/3, and c is 1. So integrating this means we're really integrating this. I guess I can rewrite this. So I'm just gonna erase this and say we've got 3 times the integral of this, which is the same as this. 2/3 over x plus 4/3 over x plus 3 plus 1 over x plus 3 squared. Now I want to point out something because it's not a huge deal, but it's a small deal. If we hadn't factored out the 3, these numbers actually would have turned out nicer, right? In fact, I'm going to distribute the 3 back in and get the integral of 4x plus 3 dx plus the integral of 2 over x plus 4 over x plus 3 plus 3 over x plus 3 squared. So sometimes it makes sense to actually not factor a constant out. Yeah, so someone's asking you this highest power coefficient tactic is considered a rule that can be used often in these types of problems. Yes, you can always do what's called equating coefficients, where you're saying in this equation here, the amount of any power of x on one side has to be the same as the amount of that power of x on the other side. It's always true. We'll do another one where we kind of abuse that tactic even more. Let's finish this problem though. So we've got, let's see. So we're going to get 4x squared over 2, so 2x squared plus 3x plus the integral of 2 over x is 2 natural log of the absolute value of x. The integral of 4 over x3 is 4 times the natural log of the absolute value of x plus 3. And the integral of 3 over x plus 3 squared, well, that's 3 times x plus 3 to the minus second. And to integrate that, we're just going to use the anti-power rule and get 3 times x plus 3 to the minus 1 divided by minus 1. Right, if we did the u substitution here, you just have u equals x plus 3, and d would just be dx, so there wasn't any constant you have to worry about multiplying or dividing by. So that's how you do this problem. It's a little bit of a mess, right? There's a lot of pieces moving here, but in the end, it's the same kind of thing. Let me show you guys another partial fractions problem. So let me grab it here. There's one specifically I want to show you. I think I know where it is. No, I will just make one up. Let's see. I think I might have to make one up, which is all right. Yeah. Okay. Sure. Let's do something like this. Give me a minute to make one up. I'm going to hide the word from you guys. Just 1 sec. I don't want to make it too terrible. I'm trying to make it not awful. Let's see. Sorry, 1 second here while I figure this out. All right. Sometimes things are funky like this. So this is going to be that's interesting. Oh, that's fine. Okay, yeah. So assuming I'm not messing it up, I'm going to have the following. So I'm going to have the integral of 3x cubed plus 4x squared minus x minus 4 divided by x to the 4th plus 4x cubed. Just double check and make sure I'm not making a dumb mistake. X cubed plus 4x squared. Should be right. Okay. I mean, either way it'll work. It's just hopefully the way I set it up, the numbers will not be terrible. All right, so this is probably partial fraction, but let's double check that we can't do a u sub. So if I let, well, it's not going to be u sub, right? So if you let u equal the bottom, you're going to get du is 4x cubed plus 12x squared, and no, it's just not going to work, right? You have a 3x cubed, you have a 4, it's not going to work. So let's try a partial fraction. So we can factor this. So we get 3x cubed plus 4x squared minus x minus 4 divided by, this factors as x cubed times x plus 4. So we're going to have to write 4 terms here for our partial fraction decomposition. We have a over x plus b over x squared plus c over x cubed plus d over x plus 4. So we're going to multiply everything by this common denominator. So multiplying it here, we obviously get the denominator canceling, so we get 3x cubed plus 4x squared minus x plus 4. We multiply it by here, one of the x's cancel, so you get a times x squared times x plus 4. When you multiply by here, two of the x's cancel, so you get b times x plus 4. Multiplying it here, all of the x's cancel, so you get, well, all the x cubed cancel, so you get c times x plus 4. Multiplying it here, the x plus 4 is canceled, and you get d times x cubed. All right, so now let's use our convenient values first. Always, 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 if you have convenient values, meaning things that make a lot of things 0, you should always use those first. I'm going to pick x equal to 0. I get 0 plus 0 minus 4 equal to 0 plus c times 4 plus 0. So that's going to give me c equal to -1. I'm also going to pick x equal to -4. Picking x equal to -4, let's okay, and a little more space. X is -4. I'm going to get 3 times -4 cubed. I guess that's going to be kind of gross. So it's going to be 3 times -64. 4 times -4 squared is 4 times 16, which is 64. Minus -4 minus 4, so that's going to be plus 4 minus 4, which is going to be 0. So I'm not going to write that part down. So I get the plus 4 and the minus 4. And that's going to equal a times 0 plus b times 0 plus c times 0 plus d times -64. Let's divide both sides by 64. So dividing this by 64, you get 3 times -1 plus 1 equals d times -1. Well, that's a lot nicer. So then -3 plus 1, which is -2. So -2 equals -d. So d equals 2. But now we have run out of convenient values. So this is where I start using what I call equating coefficient. Well, not just me, lots of people call it equating coefficient. Right? I did not come up with this. This is a very standard method of doing things. So I look for the highest power of x. Highest power of x on either side is going to be x cubed. So on the left, I have 3x cubed. On the right, I would have an ax cubed because ax squared times x is ax cubed. I don't have any bx cubed. I don't have a cx cubed, but I do have a dx cubed. So that means a plus d equals 3. And since I know that d is 2, a has to be 1. Okay, I'm still not done, so let's go down to the next highest power of x, which is x squared. X squared is going to be a little bit more challenging. So I have a 4x squared on the left. I have an a times x squared times 4. So I have a 4a x squared on the right. I have a b times x, so I have a bx squared. I don't have a cx squared. I don't have a dx squared. So this is it. So I know that 4 has to equal 4a plus b. But a is 1. So 4 equals 4 plus b. So b has to be 0. Okay. Now we rewrite our integral, which I've run out of room to do. I guess I can write it in here. I can make it fit. So this is going to equal the integral of a, which is 1 over x, plus b over x squared, but b is 0, so I don't get that term. And then c is -1, so -1 over x cubed. and then plus d, which is 2 over x plus 4. And then we integrate. So we get the integral of 1 over x is the natural log of the absolute value of x. The integral of x to the minus third is x to the minus second divided by minus 2. And the integral of 2 over x plus 4 is 2 times the natural log of the absolute value of x plus 4. So yes, equating coefficients is a tried and true standard method that I personally like to use after I have run out of convenient values of x that makes lots of things 0. Essentially each factor gives you a convenient value of x. So x plus 4 gives you x equal to negative 4. X to the third gives you x equal to 0 as your 2 convenient values here. Yeah. Okay. Let's see. So people have questions about the quiz. I suppose that's a good time to go ahead and look at the quiz. Most people will have more questions about the second question, but there were questions about the first one. So let's do the whole quiz. I'll post the solutions too, but let's go ahead and work through it just because it is they're good questions. But sure. Let's go ahead and start with the second question since we're already in the partial fractions mindset. So here we have the integral of 3x cubed minus 4x plus 2 divided by x squared times x minus 1 squared. So it is a partial fractions problem, and we're going to write it in the following way. So we're going to write 3x cubed minus 4x plus 2 over x squared times x minus 1 squared equal to a over x plus b over x squared plus c over x minus 1 plus d over x minus 1 squared. And then just like before, just like every time with partial fractions, you're going to multiply the entire equation by this common denominator. So we're multiplying everything by x squared times x minus 1 squared. Here we're going to get your numerator. So you're going to get 3x cubed minus 4x plus 2. And multiplying here, so this is where I write some things cancel. So we multiply this by this, the x cancels. And you get a times x minus 1 squared. Multiplying this by this, the x squared cancels. So you get just b times x minus 1 squared. This times this, one of the x minus 1s cancel. So you get c times x squared times x minus 1. Multiply this by this, the x minus 1 squareds cancel. So you get d times x squared. And then we're going to use our tried and true methods. First, we're going to pick convenient values. The convenient values of x are x equal to 0 and x equal to 1. I should move the chat here just a tiny bit. I always end up covering up the chat. So let's see here. So setting x equal to 0, we're going to get 2 on the left. We're going to get 0 plus b times 1 plus 0 plus 0. So b is equal to 2. Great. Let's plug in x equal to 1. On the left, I get 3 minus 4 plus 2, which is going to be 1. On the right, I get 0 plus 0 plus 0 plus d times 1. So d equals 1. Great. Now we've run out of convenient values. We have to equate coefficients. So I will say, you don't have to equate coefficients. The other route people take, which I am not going to take, is just to pick other values of x. So you can pick like x equal to 2, x equal to 3, plug those in, get some equations, plug in your node values for b and d, and then solve for a and c. But it's usually more work that way. Grading coefficients. So just to kind of point out, what I'm really doing is I'm not multiplying the whole thing out. I could. Let me actually show you. So I'm saying I know that I have for x cubed, which is my highest part of x. On the left, I have a 3x cubed. On the right, I would have a times x squared, which would be a times x cubed. I would not have any b times x cubed. I would have a c times x cubed, though. knowing, oh, I don't actually know either of those. I don't know A or C, so I need to move. So I'm going to come back to that. It's still not, it's not like wasted effort there. I just need more information. So let's look at x squared. So I don't have any x squared on the left. That's okay. I have 0x squared on the left. On the right, do I have any a times x squared? Well, this is where I have to be a little bit more careful. So if you actually multiply this out, you have a times x squared minus 2x plus 1. And then when you distribute this, you do get an ax times a negative 2x. So you do get ax cubed, and then you get a minus 2ax squared. So my coefficient of x squared on the right, here at least, is a minus 2a. I do also get, sorry, I'm just, that's what's a. I get a bx squared. I get a minus cx squared, because when I distribute this, right, I get a cx squared times a minus 1. And I get a dx squared. Okay, so now we have enough information, because I know what b and d are. So I can say that 0 equals negative 2a plus 2 minus c plus 1. And then I can substitute and say, I can take this equation and say, okay, c is equal to 3 minus a. I can plug that in over here and say 0 equals, let's see, negative 2a plus 2 minus 3 minus a plus 1. Let's see what we get. We get 0 equal to minus 2a. 2 minus 3 plus 1 is 0. Right? 2 minus 3 is negative 1 plus 1 is 0. And then a minus a is a plus a. So I end up getting 0 equal to negative a, so a equals 0. It's not very exciting. Then if a equals 0, we also know what c is. A plus c is 3. C equals 3 minus a, so c equals 3. I do want to point out what I really am doing here is that I'm equating the coefficients, but I'm not kind of multiplying the whole thing out, right? We totally could, if we wanted to, actually multiply the whole right side out here. I'm going to erase, I don't really want to erase this. I guess I'll erase this for now, and we'll come back to it. So if you multiply out the whole, so here's what I'm really saying. 3x cubed minus 4x plus 2 equals, so this is ax times x squared minus 2x plus 1. This is b times x squared minus 2x plus 1. This is cx cubed minus cx squared. This is dx squared. Multiplying this out further, right? This is ax cubed minus 2ax squared plus ax plus bx squared minus 2bx plus b plus cx cubed minus cx squared plus dx squared. So then, right, if you're looking at the different coefficients, you'd say, okay, well, x cubed, so this is equal to a plus c times x cubed, and then x squared is equal plus negative 2a plus b minus c plus d x squared. And you can even look at the x's and so on, right? You can say you have let's see, ax minus 2bx. So a minus 2b times x, and then your constant term is b, it's just b. So then b has to equal 2, and a minus 2b has to equal negative 4. But since b is 2, you have a minus 4 equals negative 4, so a has to be 0. And then this one, which we'll skip, and then a plus c has to equal 3, but since a is 0, c has to be 3. And then this one lets you solve for d. So, right, you could exclusively use equating coefficients. I don't recommend it. I definitely recommend using your convenient values first, and then if there's still things left to find, then we use equating coefficients. All right, now to actually finish the problem, we're going to be integrating A was 0, so we don't have any zero. We have 0 over x. B was 2. C was 3. And D was, I forgot what D was. And I erased it too. Hi, James, erasing things. How silly. You remember what D was? D. Thanks, Madison. Appreciate it. And D is 1 over x minus 1 squared. So then, right. So I would probably either rewrite or at least rethink of this. I would rewrite it as 2 times x to the negative second plus 3 over x minus 1 plus x minus 1 to the negative second. So then we end up with 2x to the negative first divided by negative 1 plus 3 natural log of the absolute value of x minus 1 plus x minus 1 to the negative first over negative 1 plus c. And then if you like, and I do like, you can rewrite this as negative 2 over x plus 3 natural log of the absolute value of x minus 1 minus 1 over x minus 1. Not necessary, but it is, I think it looks nicer. It's really not necessary. Okay. So let's talk more about, let's finish the quiz. Like I said, let's do the first 2 problems from the quiz, which are, I think, probably easier problems. Let's take a look at them. First one is we want to integrate x cubed e to the x. This is definitely an integration by parts problem. Specifically, we can use the tabular method here. So we can make our u and our dv columns. Our u is going to be x cubed, and the derivatives are 3x squared, 6x, 6, and 0. Our dv is the e to the x, and the antiderivatives of that are all just e to the x. And we multiply like that, and it's plus this product minus this product plus this product minus this product. So this integral is equal to x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. Bonus question. What if we asked for the integral from negative infinity to 0 of x cubed e to the x dx? Okay. Oh, right. I agree, Marshall. When the tabular method works, it's like, oh, that's great. Unfortunately, it only works for this or for like x cubed times cosine or for x cubed times sine. But when it works, it is very nice. So if we had to do this improper integral from negative infinity to 0 of x cubed e to the x, I would start first by writing a limit. So we have the limit as x goes to minus, sorry, not x, we don't use x, we use something other, anything else would be fine, not x. Limit is a goes to minus infinity of the integral from a to 0 of x cubed e to the x. Then we would do the integral, which we have already. So say, okay, this is equal to the limit as b goes to, sorry, as a goes to negative infinity of this whole thing here. X cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x. We don't need the plus c because it's a definite integral from a to 0. So then we plug in. We get the limit as a goes to minus infinity. Plugging in 0, we get 0 minus 0 plus 0 minus 6 e to the 0, which is 1. minus, we plug in a, we get a cubed e to the a minus 3a squared e to the a plus 6a e to the a minus 6 e to the a. Okay. So I would rewrite this to make it a little bit easier to see what's happening. I would write this as the limit as a goes to minus infinity of minus 6 minus a cubed over e to the minus a plus 3a squared over e to the minus a plus 6, sorry, minus, I'm distributing that minus sign, 6a over e to the minus a plus 6 over e to the minus a. Now here's the thing. A is going to negative infinity. Negative a is going to positive infinity. So e to the negative a is going to e to the infinity, which is also going to infinity. So I have 6 divided by infinity. That goes to 0. I have 6a divided by e to the negative a. So even though the top is going to negative infinity and the bottom is going to infinity, the bottom is going to infinity much, much, much faster than the top is going to negative infinity. This is also going to be 0 because an exponential function always overpowers a polynomial function. Same deal here. 3a squared is going to infinity. E to the negative a is also going to infinity, but much, much, much faster. So this fraction, the denominator is growing much more quickly. So the fraction is getting smaller and smaller and smaller. Same deal is true here as well. So we end up getting negative 6. So this integral converges to negative 6. But there was something else I wanted to mention here. I guess not. Oh, let me ask you guys. I know I asked you last week. Just want to check in again. Have either of your teachers said anything about L'Hopital's rule? Is the answer no? It's never good to ask is the answer no, because you're like, no. I'm like, do you mean no, it's not, or no, it is? Yeah. I'm assuming you mean no, they have not talked about L'Hopital's rule. So for problems like that, yeah, the answer is no. So I don't really think you'll probably be asked to do something like that, but if you are, you should go with the explanation that, yeah, the exponential thing, e to the x, gets bigger faster than like x to any power. So it's always going to overpower that. Let's look at the other question from the quiz, just because I know there were questions. So we have the integral of 2x plus 1 times e to the x squared plus x. So most of the point of this first question, parts A and B, was just to point out that even though both of these problems are mixtures, right? You have some powers of x times some exponential thing. One of them was integration by parts, and one of them was u substitution. This one's a u sub. With u equal x squared plus x, our du is exactly 2x plus 1 dx. So we can rewrite this as the integral of du times e to the u. And the integral of e to the u is e to the u, which is going to be e to the x squared plus x. That's all there is to this one. I will mention, just because it's kind of interesting, there is an alternate choice you could make for this problem. It's kind of funky. You could, if you wanted to, let u equal e to the x squared plus x. Then your du is the derivative of this, which is e to the stuff times the derivative of the stuff, dx. That's exactly your entire integral. So here you can rewrite this as just the integral of, well, all of that's my du. The integral of 1 du is u, but u is just this, which is the same as that. I don't recommend doing it this way, but some people will definitely in the past be like, hey, James, couldn't you let u equal the e of the thing? And it is true. Sometimes that does work. Okay, let's talk more about improper integrals, because I feel like that's where we kind of left off last time, and we definitely didn't get to finish talking about it. And last time we mostly talked about the type that have an infinite interval. So for example, things like this. The integral from 2 to infinity of 1 over x natural log of x. So problematic at infinity. So we're going to write this as the limit as b goes to infinity of the integral from 2 to b of 1 over x natural log of x dx. Now here's my reality. I really don't want to have to write the limit of the integral from 2 to b while I'm doing whatever process I have to do. If it's a very straightforward, like if I can do this integral in one step, great. I will do this is equal to, whatever the antiderivative of this is, evaluated from 2 to b with a limit in front of it. The problem is it's not a one-step integral. Right? I don't know the antiderivative of that just straight away. So I have to do like a process, and I really don't want to carry all of this with it as I do the antiderivative of that. So what I like to do when I have, especially with improper integrals, when I have to either do a u-sub or integration by parts, I personally like to do that off to the side. Meaning I'm going to do the indefinite integral just all by itself. So I'm going to do a u-sub here. I'm going to let u equal the natural log of x. And the reason that's a good choice is because the derivative of that is 1 over x. And I definitely have a 1 over x dx. So I'm going to plug in, I'm going to replace the 1 over x dx with my du. So that's going to become the integral of du. And I've got a 1 over u. So that's going to be the natural log of the absolute value of u, which is then going to be the natural log of the absolute value of the natural log of x. We don't worry about the plus c here because it's just the work on the side for our own use. So then we say, okay, the limit from b to infinity of the integral from 2 to b of 1 over x natural log of x dx is, the limit as b goes to infinity of the natural log of the absolute value of the natural log of x from 2 to b. And then we plug in the limits of integration. We get the limit as b goes to infinity of the natural log of the absolute value of the natural log of b. And I mean absolute value here, minus the natural log of the absolute value of the natural log of 2. So let me ask you guys, as b goes to infinity, what happens to the natural log of b? Does it go to some specific number, or does it also go to infinity? That's a good question. We think about the graph of the logarithmic function. Which has an intercept at 1, 0. Although it goes very, very slowly, it does just keep getting larger and larger and larger and larger and larger and larger and larger. So as b goes to infinity, the natural log of b also goes to infinity. And then as the natural log of b goes to infinity, the natural log of the natural log of b also goes to infinity. So basically, if you have a logarithm, if the insides are getting infinitely large, the function is getting infinitely large. So this is going to infinity. This is some constant that I don't care about. This is going to be infinity. So we have a divergent integral. I'm going to ask a slightly different question, which is going to require almost zero amount of work. What if instead we have the integral from 1 to infinity of 1 over x natural log of x dx? Well, we have additional problems. In addition to infinity being an issue here, 1 is also an issue. So the natural log of 1 is 0. We have division by 0. So although this is going to diverge because the other one diverged, we have to do a little bit. There's this extra step we have to take first. We have to break this up. We have to write this as the integral from 1 to pick any point you like. I'm going to pick 2. Plus the integral from 2 to infinity of 1 over x, natural log of x. And then I'm not going to write all the same workout, but then you can say, well, you can pick either one to work on first. I'm going to pick this one. From the work on the other side of the board, we know that this integral diverges. Since this diverges, it does not matter what this does. The whole thing is divergent. So if you have an integral that you have to break up into multiple parts, if one part diverges, you are done. The whole thing diverges. There's another example. The integral from negative infinity to infinity of x e to the x. Definitely have a problem, right? Definitely have to break this one up, right? Whenever you have a negative infinity to infinity, you have two different problem limits of integration. You always have to break it up somewhere in the middle. Usually we break it up at 0 because that's kind of the natural middle, but you can actually pick anything you want. You break it up at 1 or 3 or pi or 8. I'm going to pick 0. So this is the integral from negative infinity to 0 of x e to the x dx plus the integral from 0 to infinity of x e to the x dx. And now is where it's a really good idea to have an idea of what's happening. So I know that as x gets really, really big, that's going to be big and that's going to be big. So this function is going to get super big as you go to the right, which means I would probably guess that this one has a good chance of diverging. On the other hand, this same function, as you go way to the left, is actually going to get super, super tiny. Because while so when I say tiny, I mean close to 0, right? I'm not saying it's going to get really, really negatively large. I'm saying it's going to get very, very small, close to 0. You're going to get negative infinity for x, but then e to the negative infinity is 1 over e to the infinity, which is a super small number. And it's going to overpower that big number there. So this is getting really, really small. So this one probably has a chance of converging. And so here's the deal. If you have to break this up into multiple integrals, you should always try and you're going to have to integrate the thing to figure out what's going on. You always want to pick the one, if you can, that you think might diverge. Because if it diverges, you are done. You get to stop. You don't have to do any more work. If one piece diverges, the whole thing diverges. So let's look at that piece. And again, this is like some integration by parts. You could use the tabular method here, but it's a one-step tabular. So I will use the tabular if you guys want to see it. U is x. My derivatives are 1 and 0. dv is e to the x, e to the x, e to the x. You get x e to the x minus e to the x. So this integral, which I'm dealing with here, the integral from 0 to infinity of x e to the x dx equals the limit as b goes to infinity of the integral from 0 to b of x e to the x dx. And then that's going to be the limit. I'm running out of room. It's going to be the limit as b goes to infinity of the integral of x e to the x, which is x e to the x minus e to the x, from 0 to b. Plugging in b, we get the limit as b goes to infinity of b e to the b minus e to the b. And then plugging in 0, you get minus 0 minus 1. Okay, now here's kind of there's a kind of a little bit of sticky point here. If you plug in infinity, you get infinity times infinity minus infinity. But infinity minus infinity is what? It's indeterminate. Sometimes infinity minus infinity is 0. Sometimes infinity minus infinity is 2. Sometimes infinity minus infinity is infinity. It can actually literally be anything. In this case, it happens to be infinity. And the way you can see it is by doing some factoring. From this part here, if I factor out e to the b, you get the limit as b goes to infinity of e to the b times b minus 1, and then plus 1 over here. And now, oh yeah, if b is going to infinity, e to the infinity goes to infinity, b minus 1 goes to infinity, and infinity times infinity is infinity. So this diverges. But since this piece diverged, it doesn't matter what this piece is doing, the whole thing diverges. So I will emphasize that strongly. If you have to break your integral up into multiple pieces, you always want to, and it's not always super obvious, but if you have a guess, if you think, oh, it looks like that piece might diverge because the insides are getting really big, that's the one you should do first. Sometimes it converges, sometimes they both converge, and that's literally, if they both converge, you have to do them both. But sometimes they don't. Let's see. Oh yeah, let's look at some. So these are all the infinite interval variety of improper integral, but there are other types. Like well, in fact, like this. The integral from 1 to 2 of 1 over x natural log of x. I know we already did the 1 over x natural log of x one, but now we have the other piece of it. We're like, okay, well, so this one, it is improper because that function is undefined at 1. So here I would write this as the limit as a approaches 1 of the integral from a to 2 of 1 over x natural log of x dx. Now, when it's not an infinity that you're replacing with an a or a b, there is an extra thing we like to consider. Our interval is from 1 to 2. So we are in here. Right? We are only between 1 and 2. We're not out here. We're not out here. So if we only live in here, what side of 1 are we on? Are we on the right side of 1 or are we on the left side of 1? Give me an R or an L or a right or a left. Yeah, we are definitely on the right side of 1, which means we write the limit. We should write the limit as a approaches 1 from the right. That's something most people will do. And it usually doesn't make a difference, but it actually, technically it does matter here. And here's why it matters. So it matters in that it's correct to do it this way. It doesn't really matter in that it almost never affects your calculation. That said, teachers will probably still look for it on the test. It matters because, oh no, actually it doesn't actually. I mean, it matters here still to be right, but it doesn't matter for the reason I thought it mattered. So sometimes it matters because the function you're looking at isn't defined on the other side of the limit or the value you're approaching. So we're going to iterate this, which we've already done. We already know it's the natural log of the natural log of x. So this is going to be the limit as a approaches 1 from the right of the natural log of the absolute value of the natural log of x from a to 2. We take the limit as a goes to 1 from the right of the natural log of the absolute value of the natural log of 2, which is just a constant. I literally have no care what this is. All I know is it's a constant, so it's not going to affect whether it converges or diverges, minus the natural log of the absolute value of the natural log of a. Okay, so now we have to ask ourselves, what happens to our good old natural log function as a goes to 1? So as a goes to 1, the natural log of 1 is 0. So it actually matters a tiny bit because technically we're approaching 1 from the right. So if you think about your natural log function, right? we're approaching 1 from the right. So the function is getting closer and closer to 0, but it's getting closer and closer to 0 from the positive side, which doesn't matter because then, well, I guess it doesn't matter because I have the absolute value, so it's fine. Then this is going to 0. So what happens to the natural log function when the insides go to 0? Well, when the insides go to 0, your function goes to negative infinity. So this diverges to infinity. Let's do more. I guess it's time to start. Let's start using more of the orange pens. My least favorite pens, but I have like 20 of them. The orange ones are just, orange is not my color. Blue is my color. As any of you that have ever watched the video of class probably have noticed, I almost exclusively wear blue shirts. You might not have noticed, that's also fine. I definitely, when I was a student, was like, oh, my teacher's wearing blue again today. What a coincidence. No, I never noticed anything about my teacher wearing anything. But orange is not my color. Blue is my color. So let's look at this next one that I actually don't have. Let me grab examples here. Improper, yeah. Oh, that's a good one. We'll do that one in a minute. So let's say we have something like, yeah. So most of these improper integrals that are undefined somewhere in the interval, usually it's because there's some sort of vertical asymptote. So let's say we have the integral from like, I don't know, -3 to 2 of 1 over x. 1 over x squared. 1 over x is a little less exciting. So it's really easy to do this problem wrong. If you're not paying attention, you'd be like, oh, well, I know how to anti-differentiate 1 over x squared. This orange pen does not look like it's showing it very well. So I feel like some of the orange pens are really bright and some of them are really kind of like muted. Let's see. So this is the integral from -3 to 2, x to the -2nd. Integral of x to the -2nd is x to the -1 over -1 from -3 to 2, which is just -1 over x, -3 to 2, which is -1 over 2 minus -1 over 3, which is -1/2 plus 1/3, which is, I don't know, like -1/6 or something, I think. No, none of this is right. Everything I just wrote was total garbage. The reason it's total garbage is because this function is undefined somewhere on this interval, right? In fact, I shouldn't be able to do the negative area here because we'll take a look. 1 over x squared is always positive. So something like this, vertical asymptote, and something like this. So if I go from, -3 to 2, well, I definitely shouldn't be getting a negative answer, right? That's a positive amount of area. So there's something wrong with what I've done. And the thing that's wrong is I haven't accounted for the fact that it's undefined at 0. So just like in other problems, we're going to break this integral up at the problem point. So it's always kind of a bummer when your interval, where your function's undefined somewhere in the interval, because then you have to write 2 intervals. And it's much nicer if it's one of the endpoints, but sometimes it isn't. So we're going to write this as the integral from -3 to 0 of 1 over x squared dx plus the integral from 0 to 2 of 1 over x squared dx. And I can't stress enough, I really do recommend dealing with kind of just one of these at a time. Or you can, if you want to, you can be like, okay, this is the limit as b goes to 0 from the left of the integral from -3 to b of x to the -2nd dx, plus the limit as a goes to 0 from the right of the integral from a to 2 of 1 over x squared dx, or x to the minus second. But the thing is, right, you really want to do these one at a time to save yourself some work. You can do both of them, and sometimes you will, right? Like if the whole thing converges, which this one doesn't, but if the whole thing converges, then you do have to do both integrals. But here, I'm just going to look at, let's look at this one. When I look at the limit, this b goes to 0 from the left, and it is 0 from the left, right? Because we're between -3 and 0. We are on the left side of 0. Integral of x to the -2 is x to the -1 over -1 from -3 to b. I would much rather write x to the -1 as 1 over -x or -1 over x. So its limit as b goes to 0 from the left of -1 over x from -3 to b. When we plug in b, we get -1 over b minus -1 over 3. But as b goes to 0, this goes to -1 over 0, which goes to some sort of infinity. Specifically, it goes to positive infinity because it's a -1 over a small negative number. So this is going to blow up to infinity. So you're going to get infinity. So this diverges, which means we don't even care what this does. It also diverges. So the whole thing diverges. But you don't have to know. Once you know this diverges, stop. You've done enough. You don't need to look at that at all. Let's look at some more examples. Yeah. How about the integral of, sure, integral from 2 to 6 of 1 over the square root of x minus 2. So where is this function undefined? Let me rephrase. Where in this interval is this function undefined? I will mention this function is undefined lots of other places, right? Actually, this function is undefined for any value that is less than or equal to 2. If you plug in 1, you get 1 minus 2, that's the square root of the negative. So, but we only actually care where it's undefined on the interval. We don't care that it's undefined at negative, at 1 or 0 or any negative number, because those aren't what we're looking at for the integral. So we're going to write this as the limit is a approaches 2 of the integral from a to 6. And I'm going to rewrite this as x minus 2 to the -1/2. And we are approaching 2 from the right-hand side. Because if we're between 2 and 6, we're definitely bigger than 2. Which actually does matter here, right? If you approach 2 from the left, that limit wouldn't exist. Right? It's actually kind of interesting. If you ever see, like, just as a quick aside here, and someone says, like, hey James, what's the limit as x approaches 2 from the left of the square root of x minus 2? Like, hey, that limit does not exist. Because you can't plug in numbers smaller than 2 into the square root of x minus 2 and get real results. So it does matter which side you approach 2 from, especially in this one. So we're going to integrate. So the limit as a approaches 2 from the right. The integral of x minus 2 to the -1/2. So what I'm really doing here that I'm not writing down is I'm treating this like a u substitution. But then if u is equal to x minus 2, then my du is just dx. So I know how to integrate u to the -1/2. It's u to the 1/2 divided by 1/2, which is just 2 times u to the 1/2. So it's going to be 2 times my u to the 1/2. But I don't think you actually need to do the u substitution here. Right? If your u would just be x plus or minus something, just kind of treat your x plus or minus something like x and integrate like you normally would. So right, you get x minus 2 to the positive 1/2 divided by 1/2, which is times 2, from a to 6. Then we plug in. Plugging in 6, you get 2 times 6 minus 2 to the 1/2 minus plugging in a, you get 2 times a minus 2 to the 1/2. All right, and now you let a go to 2. So if a goes to 2, 2 minus 2 is 0, and 0 to the 1/2 power is perfectly fine. 0 to a positive power is just 0. So I end up getting 2 times 4 to the 1/2 power. Square root of 4 is 2, 2 times 2 is 4. So if you end up, basically, if you end up doing one of these improper integrals and you're getting 0 to a positive power, you're set. Then you're getting 0 to a negative power, you're screwed. Not screwed. The integral does not converge. So this integral converges to 4. Let's look at kind of two different problems. Oh, it's not okay. Yeah, I got it. Let's look at the integral from, yeah. Is that gonna work around? Yeah. Let's do from, sorry, brain work, 2 over cube root of x minus 7 from, yeah, fine, from 6 to 15 versus the integral from, actually, let's make it the same, 6 to 15 of 2 over x minus 7 cubed. So here's what I want to point out. Both of these functions are undefined as 7, right? Well, I should say both of the functions you're integrating, right? This function undefined at 7 because you divide by 0 and plug in 7. This also undefined at 7 because when you plug in 7, you divide by 0. But here's what I want to emphasize. When you integrate this, right, you've got 2 over x minus 7 cubed. When you integrate this, you're going to get something like something over x minus 7 squared. Right? Because the integral of 2 times x minus 7 to the minus third is going to give you 2 times x minus 7 to the minus second divided by minus 2. Whereas here, your 2 times x minus 7 to the negative 1/3. When you integrate that, you're going to get 2 times x minus 7 to the positive 2/3 divided by 2/3. So check this out. When you plug in 7 to each of these functions, you get division by 0. After you integrate each of them, plugging in 7 here, you'll no longer be dividing by 0. You'll have 0 to a positive power. Plugging in 7 here, you still will be dividing by 0 because you'll have 0 to a negative power. And 0 to a negative power is like division by 0. Right? I would probably rewrite this one as 2 over negative 2 times x minus 7 squared. So basically, if your initial power is kind of negative but not too negative, when you integrate it and add 1 to the power, the new power is positive. And then plugging in something that makes it 0 is okay. But if your original function, if your power is too negative and you integrate it, it's still negative, then when you plug in something that makes it 0, it's still undefined. So I know it's kind of a lot of words to say, but when you look at something, you can probably have a guess as to whether, especially ones where they're undefined somewhere in between, you can have a pretty good guess as to whether it's going to converge or diverge. I'm pretty sure this one's going to converge because I know when I anti-differentiate this function, I no longer have division by 0 as a possibility. To do this, we have to break it up. Actually, let's do that one first. So I'm going to break this one up. at 7. So I'm going to do write it as the integral from 6 to 7 of 2 times x minus 7 cubed dx plus the integral from 7 to 15 of 2 times x minus 7 to the negative third dx. Let's look at this one specifically. This is going to be the limit as b approaches 7 from the left of the integral of 2 times x minus 7 to the negative third from 6 to b. And then we take the, sorry, 1 second, it's hot here. So integrate this, the limit as b goes to 7 from the left of 2 times x minus 7 to the minus 2 divided by minus 2 from 6 to b. We cancel a 2 and then 2. This is going to be the limit as b goes to 7 from the left of negative b minus 7 to the negative second minus negative 6 minus 7 to the minus second. And b minus 7 to the minus second, well, if you plug in 7, 7 minus 7 is 0. 0 to a negative power is division by 0. So this is going to diverge to some sort of negative infinity. So this one diverges. Right? I didn't even check this. Because once one piece diverges, the whole thing diverges. That piece could converge. It wouldn't matter. It doesn't, but it wouldn't matter. This one, on the other hand, we're going to break up also. So I write this as the integral from 6 to 7 of 2. Let's be smart about it. Let's write it as 2 times x minus 7 to the minus 1/3 plus the integral from 7 to 15 of 2 times x minus 7 to the minus 1/3. I do want to point out that unlike the problem on the previous side where we had a square root, cube roots you can take cube roots of negatives or positives. So it's perfectly okay that your insides here are negative some of the time. Perfectly fine. So let's see what we do here. That's a lot of writing. That's the problem. The ones where you break them up and they actually just converge, it feels like a lot of effort. Let's go ahead and erase this. We don't need this anymore. First. So let's see. So let's do this part first. This is going to be the integral from, sorry, the limit as b goes to 7 from the left of the integral from 6 to b of 2 times x minus 7 to the minus 1/3 dx. That's going to equal the limit as b approaches 7 from the left. Integrate this, you get 2 times x minus 7 to the 2/3. Divided by 2/3 is like multiplied by 3/2 from 6 to b. And then we plug in, we're going to get the limit as b goes to 7 from the left. 3/2 times 2 is 3 times b minus 7 to the 2/3 minus 3 times 6 minus 7 to the 2/3. When you plug in b, being 7, 7 minus 7 is 0, 0 to a positive power is 0. So this part's 0, and this part's going to be minus 3 times minus 1 to the 2/3. And minus 1 to the 2/3 is 1, so minus 3 times 1 is just minus 3. Okay, now I have to do the same thing for this part. Now the nice thing is we've already done most of the work. Right? We know how to integrate this, it's just going to be that. So you could totally write this as the limit as a, sorry, and then really it's just this part is equal to that. It's kind of right, not the best notation there. This is the limit as a approaches 7 from the right of the integral. This, but we know the integral of this is 3 times x minus 7 to the 2/3. And a will be the bottom limit, 15. So we plug in our limits of integration. We get the limit as a goes to 7 from the right of 3 times 15 minus 7 to the 2/3 minus 3 times a minus 7 to the 2/3. 7 minus 7 is 0 to the 2/3 is still 0. 15 minus 7 is 8. 8 to the 2/3 is 4. So you get 3 times 4, which is 12. So our total answer is that this converges to 9. 12 minus 3. All right. One last thing. Sometimes this is more, I feel like people have said this in other classes when I was in school. This integral from negative infinity to infinity. What have I got? Sorry, brain. Sure, of x e to the negative x squared. This converges, and it converges to 0. And let me just point out. Yeah. I don't really want to do it because we're out of time, but I will just tell you that you can break this up. And show that each of these converge. You can do a u sub with a u equal negative x squared. I don't like to change the limits of integration when it's improper. So I would just do the u sub here. And basically end up getting that this is the, I'm kind of hand waving things here because we're out of time. I would do the limit as b goes to infinity. The integral of this is e to the negative x squared times a negative 1/2 from 0 to b. And then you plug in the b, and you get the limit as b goes to infinity of negative 1/2 e to the negative b squared minus negative 1/2 e to the 0. And then e to the negative infinity goes to 0. So this part goes to 0, and you're getting 1/2. So this part converges to 1/2, and then this part converges to negative 1/2. And the reason that these cancel each other out is because this is an odd function. And it looks like this. So you've got all this area over here is negative 1/2. All this area over here is positive 1/2, and they totally cancel each other out. But what I want to contrast that with, and this will just take a second, is that this integral, negative infinity of x cubed, even though x cubed is also an odd function, right? It looks like this. You have all this negative area over here, all this positive area over here. How much positive area is over here? An infinite amount. And once one part of your integral diverges, poof, you're done. The whole thing diverges. So we do not get to say that this is equal to 0. It's not. This integral is divergent because one of the pieces diverges. And we don't get to say that those infinities can't. You can't say that this positive infinity here cancels out that negative infinity there, which is unfortunate but true. So we'll leave you at that.